Imagine for a moment a universe utterly devoid of rules, not just a place where things are a little messy, but a chaotic void so complete that nothing, absolutely nothing, makes sense. There are no consistent principles, no dependable forces, no predictable patterns. In such a realm, the very concepts of up or down, hot or cold, before or after, would be meaningless. It's a space where a star might pop into existence 1 second, then vanish into thin air the next, only for a giant teacup to appear in its place. Sounds like a whimsical, impossible dream, right? Yet here we are, in a cosmos that is anything but lawless. Our universe is a breathtaking symphony of precision and order, governed by elegant physical laws so consistent and powerful that they allow colossal galaxies to swirl in grand cosmic dances, and they enable the most intricate forms of life, like you and me, to not only exist but to thrive, to think, and to wonder. The sun rises reliably, gravity keeps our feet firmly planted, and the atoms that make up everything around us behave with astonishing predictability. This incredible contrast between a potential primordial chaos and our current highly ordered reality brings us face to face with one of the most profound mysteries at the heart of cosmic origins. How on earth could such intricate, dependable order arise from such an utterly lawless, randomized beginning? This isn't merely a philosophical musing or a poetic thought experiment for late-night discussions over coffee. No, this is a central, burning question that challenges the very bedrock of our scientific understanding of reality itself. It forces us to confront a radical, almost heretical idea. What if the physical laws we observe, the very rules that dictate how everything works, weren't eternally present, fixed in place since infinity? What if instead physics itself, in all its majestic precision, actually emerged from something far more fundamental, something that initially lacked any discernible structure or predictability? This means considering the possibility that the rules of the game weren't always there, but rather came into being, evolving from a state of primordial non-existence into the sophisticated framework we see today. This journey is not for the faint of heart, for it asks us to peel back the layers of reality and peer into a realm where our current scientific models might falter. We're going to dive deep into the fascinating, mind-bending concept of a lawless beginning, exploring what that astonishing idea truly means for cosmic origins. We'll investigate theories that dare to suggest that the fabric of reality began as a turbulent, unpredictable soup before solidifying into the consistent laws that shape our world. Prepare yourselves, because this is a story that will challenge every assumption you hold about the universe and your place within it. It's a story that asks us to question the very foundations of existence, probing whether the rules we live by were predetermined or if they were, in fact, born from chaos. Get ready to have your mind expanded, because if physics can emerge from nothing, then the possibilities for what else might be possible are truly limitless. So let's try to truly picture this starting point, this cosmic canvas before the laws. Imagine a state so utterly alien to our experience that even describing it stretches the very limits of our language and understanding. Forget about empty space, because space as we know it, with its 3 dimensions and geometry, hadn't even come into being yet. Forget about time ticking forward, because the concept of a before or an after was utterly meaningless without events or change to define it. And certainly forget about matter or energy, because these building blocks of our universe were still inconceivable. This isn't just a void, it's a pregeometric or pre-physical epoch. This phrase itself hints at the profound depth of this idea. pregeometric suggests a realm where points, lines, and shapes, the very elements from which we construct our understanding of space, simply did not exist. There was no here or there, no up or down. It means that the fundamental structure that allows us to measure distances or define locations was absent. Think of it as existing before the blueprint of reality was even drawn, before the canvas itself was stretched. Without geometry, there's no framework for anything to exist within, no stage for events to unfold upon. Similarly, pre-physical implies a state before the very existence of physical properties or phenomena. In our universe, everything has physical attributes: mass, charge, spin. Things interact through forces, follow pathways, and obey conservation laws. But in this primordial state, there would have been no such properties, no forces, no interactions. It's a state devoid of any discernible characteristics that we can quantify or describe with our current physics. There wouldn't be any distinction between one thing and another, primarily because there were no things at all in any recognizable sense. It truly represents the ultimate, lawless state, a complete absence of any structure or predictability, where even the most basic elements we take for granted simply weren't part of the picture. Understanding this initial condition is not just an academic exercise. It's absolutely crucial if we're to grasp how anything, let alone the intricate cosmos we inhabit, could have subsequently emerged. If we start with something, anything, then we're automatically assuming some form of pre-existing structure or rule. But to truly tackle the question of laws emerging, we have to push our minds to the absolute edge, to contemplate a true void of structure or predictability. It's only by acknowledging this radical starting point that we can begin to theorize how the very foundations of our physical reality, the concepts of space, time, matter, and the laws governing them, could have coalesced from such an unfathomable beginning. This is where the real mystery begins to unfold. This brings us to the first monumental mystery, the paradox of creation from nothing, or as it's often phrased in Latin, ex nihilo. If we've just described a state truly devoid of geometry, of physical properties, of even the most basic laws, then how could anything conceivably emerge from it? This isn't just a philosophical puzzle. It cuts to the very core of our understanding of cause and effect. In our familiar universe, every event has a cause, every action an antecedent. The ball moves because it was hit, the light shines because the bulb is powered. This chain of causality is fundamental to how we comprehend reality. But in a realm without laws, how can there be causality? How can one state transition into another if there are no governing principles to dictate such a change? Think about it. If there are no forces, no interactions, no inherent tendencies for anything to happen, then what provides the impetus for the first stirrings of existence? It's like asking a game to begin when none of the rules have been established, and even the players and the board don't exist yet. This paradox challenges the very notion of how change itself initiates. It forces us to consider mechanisms that operate entirely outside our conventional understanding of physics, pushing us into deeply speculative territory where our established frameworks simply no longer apply. This is where the science truly becomes mind-bending. We're not just looking for a new law, we're looking for an explanation for how laws themselves might have arisen. This isn't a problem that can be solved by simply invoking a slightly different set of initial conditions within our known physical cosmos. Instead, it demands a radical re-evaluation of what constitutes a beginning, and whether the concept of nothing can truly be nothing if something ultimately arises from it. It's a leap into the unknown, requiring us to imagine scenarios where the very rules governing existence are forged in the crucible of absolute void, leading us to truly speculative physics. One fascinating idea that grapples with this deep paradox is known as the quantum foam hypothesis. Instead of imagining a true, absolute nothingness, this theory suggests that even at the most fundamental, unimaginably small scales, reality isn't smooth and empty. Think of it like looking at the surface of an ocean from far away. It appears flat and calm, but as you get closer, you see it's teeming with tiny waves, ripples, and bubbles constantly forming and dissipating. The quantum foam hypothesis applies this idea to spacetime itself. It posits that at sizes smaller than what we can currently measure, roughly 100 billion times smaller than a proton, the very fabric of spacetime isn't continuous but rather a chaotic, turbulent sea of quantum fluctuations. In this super tiny, frothing realm, the rules of classic physics simply break down. Instead, we enter the strange and unpredictable world of quantum mechanics, where particles can spontaneously appear and disappear from existence, where energy fields fluctuate wildly, and where the concepts of space and time as we know them become blurry and ill-defined. Imagine a constant, energetic bubbling where fleeting mini-universes or transient bubbles of space and time momentarily pop into being, only to vanish again almost instantly. These are not full-fledged universes, but rather ephemeral pockets of localized energy and nascent geometry, arising purely from the inherent uncertainty and dynamism of quantum reality. This constant, spontaneous activity provides a crucial potential answer to the creation ex nihilo dilemma. It suggests that the nothing wasn't truly a void, but rather a seething, energetic, and unstable quantum vacuum filled with potential. The beauty of the quantum foam idea is that these fluctuations don't require pre-existing laws to guide them. They are a fundamental, inherent property of the quantum realm itself. This intrinsic instability, this ceaseless bubbling, could be the raw material, the primordial soup from which everything else eventually emerges. It's the universe constantly trying out possibilities, like an endless cosmic game of trial and error at an infinitesimally small scale. Each bubble, each fluctuation represents a fleeting opportunity for something more structured to form. In this view, the initial universe didn't just appear, it was constantly being tested and tried out in countless quantum iterations. The key insight here is that structure and predictability, what we call physical laws, might not be foundational. Instead, they could arise from this fundamental chaos. If enough of these transient bubbles formed, perhaps one or more of them could expand, cool, and freeze certain properties, giving rise to stable particles, forces, and eventually, the consistent laws we observe today. This concept moves beyond a static view of existence, proposing a dynamic and evolving origin where what we perceive as fundamental laws are actually the solidified patterns that emerged from this initial quantum turbulence. It's a powerful vision, suggesting that order isn't magically imposed but rather crystallizes out of dynamic, chaotic potential. Following this idea of quantum foam, a visionary physicist named John Wheeler took this concept even further, proposing what he called pregeometry. Wheeler, known for his profound insights and challenging questions about the nature of reality, suggested that space-time, the very arena in which all physical laws play out, might not be as fundamental as we think. Imagine that the smooth, continuous space and time we experience are like a woven fabric. Wheeler's idea was that this fabric isn't the raw material. It's something that itself emerges from even more basic, granular components. It's similar to how a solid wall appears continuous from a distance, but up close you see it's made of countless individual bricks. For Wheeler, space and time were not the bricks themselves, but the structure built from them. This pregeometry concept deeply resonates with the quantum foam hypothesis because it offers a mechanism for how the abstract, ever-fluctuating quantum foam could give rise to something as solid and predictable as space-time. Wheeler envisioned a deeper reality where even the foundational concepts of distance, shape, and duration, which are the bedrock of geometry, are not inherent properties but rather emergent qualities. This means that before space-time as we know it existed, there might have been a more primitive, abstract realm where these geometric properties were still in the process of forming, like an unformed clay being molded into specific shapes. The implications of Wheeler's pregeometry are nothing short of revolutionary, especially for our discussion on how laws could emerge. If space-time itself is emergent, then the physical laws that govern it, which are intrinsically linked to its geometry and structure, must also be emergent. Consider the law of gravity, which describes how masses warp spacetime. If spacetime itself is a derived property, then gravity, as we understand it, cannot be an eternally pre-existing law. Instead, it would have to be something that crystallized out of the underlying pregeometric chaos, becoming stable and descriptive once spacetime acquired its familiar properties. This transforms our perspective from seeing laws as fixed, unbreakable decrees to viewing them as patterns that solidified as the universe evolved its fundamental structure. Wheeler's vision hints at a universe that fundamentally builds itself from the ground up, with geometry and physics arising from a kind of cosmic self-organization. It's a powerful argument for the idea that order and predictability aren't imposed from an external source, but are rather an intrinsic outcome of the universe's own dynamic nature. This isn't just about the Big Bang, it's about the very essence of reality coming into being, starting from principles so fundamental they precede even the existence of space and time. This profound concept pushes us to think beyond our current understanding of the cosmos, suggesting that the universe is not merely governed by laws, but that it actively generates them. This brings us to a crucial concept in physics, often called symmetry breaking, which offers a powerful way to understand how order can emerge from something that appears chaotic or uniform. Imagine a completely featureless, perfectly symmetrical sphere. From any angle, it looks exactly the same, devoid of any distinguishing characteristics. This sphere represents a state of high symmetry. Now picture what happens if this sphere cools down and begins to freeze, forming crystalline structures. As the crystals form, they introduce specific orientations and patterns. Suddenly, the perfect symmetry is broken because distinct features now exist, like facets or edges. The sphere transitions from a uniform, undifferentiated state to one with clear, well-defined structures. Could our universe's laws have crystallized out of a featureless, highly symmetric, lawless state through a similar process? This is where the idea of phase transitions comes into play. Think of water. At high temperatures, it's a gas, steam, a chaotic collection of molecules moving freely. As it cools, it undergoes a phase transition to become liquid water, where molecules are still dynamic but maintain closer relationships. Cool it further, and it transitions again into solid ice, where molecules lock into a rigid, highly ordered crystalline structure. Each phase has its own set of rules or behaviors that govern the molecules. In the context of the early universe, this concept suggests that the initial, lawless state might have been one of ultimate symmetry, a state where all fundamental forces were unified, and there were no distinctions between particles or interactions. As the universe expanded and cooled, it would have undergone a series of cosmic phase transitions. Each transition could have broken a fundamental symmetry, leading to the emergence of distinct forces, particles, and ultimately, the physical laws we observe today. For instance, the electromagnetic force and the weak nuclear force are believed to have been unified at extremely high temperatures in the early universe, meaning they were indistinguishable. As the universe cooled, this electroweak symmetry broke, and they became two distinct forces with their own unique characteristics and rules. This idea is incredibly compelling because it provides a mechanism for how specific, observable laws could arise from a more primordial, undifferentiated state without needing to invent them from scratch. It's not about laws being imposed from the outside, but rather about them emerging naturally as the universe itself evolves through different states. These phase transitions would be like cosmic tipping points, where the underlying reality suddenly shifts its fundamental configuration, and out of that shift, new rules of interaction begin to solidify. It suggests that the laws are not static, eternal blueprints, but rather a dynamic consequence of the universe's own self-organizing processes. The elegant predictability of our cosmos, from the way light travels to how galaxies spin, could be the result of a long series of these cosmic symmetry-breaking events, each one shaping the world as we know it. This brings us to a compelling and often debated idea, the Anthropic Principle. If we accept the possibility that physical laws are not eternal and fixed blueprints, but rather emerged from a more chaotic or undifferentiated state, then a natural question arises: why these specific laws? Why are the fundamental constants of nature, like the strength of gravity or the mass of an electron, so precisely tuned to allow for the existence of stars, planets, and ultimately, life itself? It seems almost too perfect, doesn't it? The Anthropic Principle offers a provocative answer. It suggests that a universe where laws emerged might not be unique. Instead, perhaps an immense number of proto-universes, or regions of a larger multiverse formed, each undergoing its own unique series of symmetry breaks and phase transitions. In this cosmic lottery, each of these nascent universes would have crystallized its own slightly different set of emergent laws and fundamental constants. Some of these universes might have collapsed almost instantly, others might have expanded into barren, featureless voids, and still others might have been too unstable to allow for any complex structures to form. However, in this vast cosmic landscape of possibilities, there would inevitably be some universes that, purely by chance, happen to emerge with a specific set of laws and constants that are just right for complexity to build, for chemistry to unfold, and for stars to ignite the very conditions necessary for life to eventually appear. Our universe, argues the Anthropic Principle, is simply one of these Goldilocks universes. We observe our specific set of laws and finely tuned constants, not because they are somehow universally destined to be this way, but precisely because they are the only ones that could possibly give rise to intelligent observers like us. It's a bit like saying we live on Earth because it has liquid water and a breathable atmosphere. If it didn't, we wouldn't be here to observe it. This viewpoint offers a compelling, though sometimes unsettling, framework for understanding the apparent fine-tuning of our cosmos. It shifts the discussion from trying to explain why the laws are just so, to accepting that our existence itself acts as a filter on the observable universe. We are simply in the universe that permits our presence. This doesn't mean that the laws are arbitrary, but rather that their emergence was a process with many possible outcomes, and we reside in one of the successful ones. It removes the need for a preordained design, replacing it with a cosmic evolutionary selection process, where only certain combinations of emergent laws allow for the development of observational capacity. Such a perspective profoundly influences our attempt to reconstruct the story of how physics itself came to be. And this brings us to another profound mystery, one that truly pushes the limits of our comprehension, the nature of time itself. If physical laws are not eternal, if they somehow emerged from a pre-physical state, then what about time? Was there a before the Big Bang, or even a before the very first laws began to coalesce? This isn't just a linguistic puzzle or a philosophical musing. It strikes at the heart of our temporal understanding. We tend to think of time as a fundamental, ever-present river, flowing uniformly from past to future, a fixed backdrop against which all events unfold. But what if time, like gravity or electromagnetism, is also an emergent phenomenon? Imagine a state where the very concept of duration, sequence, or causality simply didn't exist. In a truly lawless beginning, the notion of before or after might be utterly meaningless. There would be no processes to mark change, no cause and effect relationships to define a sequence of events. It's a challenging idea to grasp because our minds are so deeply wired to perceive reality through the lens of time. Consider the possibility that time, as we experience it, became a meaningful concept only once certain fundamental laws or structures had solidified. Perhaps the very act of symmetry breaking, or the formation of the first stable particles, created the conditions necessary for a discernible arrow of time to emerge. For example, the expansion of the universe itself provides a direction for time, an undeniable movement from a hotter, denser state to a cooler, more diffuse one. If the universe hadn't started expanding, or if its expansion was somehow reversed, would our understanding of time be different or perhaps non-existent? This concept suggests that time isn't an independent entity, but rather a property that arises from the interactions of matter and energy governed by laws. Think of it like this: a clock tells time, but the clock itself couldn't exist without the physical laws that allow its components to function and its gears to turn. Similarly, perhaps the universe itself acted like a giant, self-assembling clock, and only once its fundamental mechanisms were in place could time begin to tick. This doesn't mean that there was literally an empty void for an infinite duration before time began. It means that the very framework for measuring duration, for defining a past and a future, simply wasn't established. This subtle but crucial distinction forces us to reconsider time not as a given, but as an integral part of the cosmic tapestry that unfolded along with everything else. This profound rethinking of time opens the door to an even more radical idea. What if reality itself isn't built on matter and energy as we perceive it, but on something far more abstract like information? This perspective, gaining traction in modern physics, suggests that the universe might have begun not as a fiery explosion of particles, but as a pure, unadulterated sea of information. Think of it like a cosmic hard drive teeming with potential and data, even before the concept of space, time, or matter had fully materialized. If that's the case, then our physical laws wouldn't be fundamental properties etched into the fabric of creation from eternity. Instead, they could be seen as emergent patterns, complex algorithms that process this underlying information. Imagine a highly sophisticated computer program. The rules of that program, the specific lines of code that dictate how it behaves, aren't fundamental to the silicon chips it runs on. They are instructions, a set of relationships that allow information to be manipulated and processed in specific ways. Similarly, in this view, gravity, electromagnetism, and the nuclear forces aren't inherent things, but rather the operational rules or protocols governing how cosmic information interacts and unfolds. This concept profoundly challenges our deeply ingrained materialist assumptions about reality. For centuries, our scientific understanding has largely been built on the premise that matter and energy are the primary constituents of the universe, with information being a secondary characteristic derived from their arrangement. But if information is truly fundamental, then the physical world, with all its tangible particles and forces, might be a complex, emergent phenomenon, much like the images and sounds that appear on your computer screen are emergent from the digital information processing within the machine. It suggests that what we perceive as solid reality might be a highly intricate pattern of bits, a cosmic data stream that constantly processes and updates itself. This doesn't mean our world isn't real. It simply redefines the nature of that reality to its most foundational level. Consider how complex systems arise from simple instructions. A snowflake forms its intricate, unique pattern based on the simple physical laws of water molecules interacting with temperature. No master plan dictates each crystal's design, only basic rules leading to emergent complexity. In an information-centric universe, physical laws would operate similarly. They would be the basic rules, the algorithms that transform raw information into the galaxies, stars, and even life we observe. This is a universe that computes itself into existence, where the logic of its operation, its physics, is a dynamic, self-organizing process. The very stability and predictability we experience in physics could be a sign of a robust, self-correcting information system that has settled into a consistent and coherent set of operational rules. It opens up the fascinating possibility that the universe isn't just described by mathematics, but that it is, at its deepest level, fundamentally mathematical, a grand computation playing out on a cosmic scale. Building on the idea of information as fundamental, let's venture into a truly mind-bending concept from quantum mechanics, the many worlds interpretation. Imagine that every time a quantum event has multiple possible outcomes, the universe doesn't just pick one. Instead, it literally splits, and each possibility becomes real in its own separate, distinct universe. It's as if every decision point in the quantum realm branches off into an entirely new reality. So when a particle's spin is measured, instead of collapsing into either up or down, the universe cleverly divides, with one branch experiencing up and another experiencing down. This isn't just a theoretical curiosity. It's a profound way of looking at reality where all potential quantum outcomes actually unfold somewhere. Now, if this is true, if every quantum possibility blossoms into its own reality, could this incredible multiplicity extend beyond just particle states and into the very fabric of physical laws themselves? If laws are emergent properties, as we've been discussing, perhaps they too are subject to this cosmic branching. Think about it. In the primordial quantum foam, or the informational sea before laws solidified, countless tiny fluctuations and interactions could have occurred. Each one, in this many worlds view, might have led to a slightly different set of emergent rules. Our universe, with its specific laws governing gravity, light, and matter, would simply be one particular branch among an unimaginable number of others. This means that in some parallel universes, the speed of light might be slower, or gravity might be stronger, or electromagnetism might operate under slightly different rules. These variations wouldn't just be minor tweaks. They could lead to fundamentally different cosmic evolutions, perhaps universes where stars never form, or where life as we know it is utterly impossible. Our universe, then, isn't necessarily special because its laws were preordained or uniquely perfect. Instead, it's special to us because these are the laws that emerged in this particular branch, allowing for our existence and the complex structures we observe. It's a bit like a giant cosmic experiment where every possible configuration of emergent laws is tried out, and we simply happen to reside in one of the successful trials. This perspective doesn't just offer an explanation for the fine-tuning of our universe. It democratizes it, suggesting that our specific laws are one outcome among an endless array of possibilities, continually being generated in the vast, ever-branching multiverse. This leads us to our third great mystery, the initial singularity and profound lawlessness. The Big Bang, our universe's dramatic cosmic birth, is typically described as beginning from an infinitely dense, infinitely hot point, a singularity. This singularity isn't just a point of extreme conditions. It's a place where our current understanding of physics completely unravels. All the laws we've painstakingly discovered, general relativity, quantum mechanics, the very rules governing space and time simply cease to apply. They break down much like a computer program crashing when it encounters an impossible calculation. This isn't just a minor glitch, it's a monumental puzzle at the very foundation of cosmology. For decades, scientists have grappled with what this breakdown truly signifies. Does it mean our theories are incomplete, or is there something far more profound at play? Consider this: instead of viewing the Big Bang singularity as merely a boundary beyond which our equations fail, what if it was a transition point? What if this breakdown of known laws wasn't a flaw in our understanding, but rather a symptom of something truly fundamental? An actual shift from a state that was genuinely lawless to one where laws began to coalesce and take shape. Imagine a universe that wasn't just starting with matter and energy, but was actively booting up its very operating system, its physical laws. This perspective reframes the singularity not just as the beginning of everything physical, but as the origin of physics itself. It's the moment where the rules of the game were being written, where the constants were being set, and where the fundamental interactions we observe today started to solidify out of an utterly undefined state. This idea profoundly shifts our understanding of cosmic origins. If the Big Bang singularity truly marks the emergence of laws, then the universe didn't just expand from a point. It evolved from a state of pure potentiality into a realm governed by elegant, predictable principles. It suggests that before that moment, there was no gravity to attract, no electromagnetism to bind, no time to flow. These fundamental forces, these constants, and the very fabric of space-time were not present and eternal, but instead sparked into being at this critical juncture. It's a radical thought, pushing us to ask whether the nothing before the Big Bang was truly empty, or if it was a fluid, chaotic state from which order, in the form of physical laws, spontaneously crystallized, laying the groundwork for everything that followed. Building on this idea of laws emerging, what if the universe's rules didn't just pop into existence fully formed, but instead self-organized, much like a complex system evolves from simple beginnings? Think about how a murmuration of starlings forms those breathtaking, fluid shapes in the sky. No single bird is leading the flock, giving orders. Each bird is simply following a few basic rules. Stay close to your neighbor, don't bump into them, and move in the general direction of the group. Yet from these incredibly simple local interactions, a stunning, complex, and highly ordered behavior emerges. The pattern isn't imposed from above, it arises from within. We see this phenomenon of self-organization everywhere in nature. Consider the intricate patterns of a snowflake, each unique, yet all following precise laws of crystallization. Or observe the swirling dynamics of a hurricane, a massive structure of incredible power and complexity, born from the interplay of temperature, pressure, and humidity. These aren't chaotic events in the true sense, they are emergent phenomena where order and complexity arise spontaneously from the interactions of countless individual components. This is a powerful concept within complex systems theory, suggesting that grand, overarching structures can be built from the ground up without needing a master plan or pre-existing blueprint. Applying this revolutionary way of thinking to the dawn of the universe, it prompts a compelling question. Could the fundamental physical laws themselves have self-organized in a similar fashion? Imagine a primordial state, even more basic than the quantum foam we discussed earlier, where particles or proto-units simply had a few very rudimentary, perhaps even random, ways of interacting. Over time, through countless interactions and feedback loops within this pre-universe, certain stable patterns of interaction might have begun to solidify. These stable patterns, essentially, would become the first rudimentary laws. Perhaps these interactions favored certain outcomes, leading to a kind of gravitational pull towards more ordered and consistent configurations. This process wouldn't be instantaneous. It would be a gradual unfolding, a cosmic dance where the rules of the game were iterated and refined through sheer volume of interaction. As these initial, simple rules started to emerge, they would then influence subsequent interactions, leading to progressively more complex and stable laws. It's a bit like how a language develops. No one sits down to invent all the rules of grammar and vocabulary at once. Instead, words and structures emerge from repeated usage and communication, eventually forming the intricate systems we call languages. In this cosmic analogy, the fundamental forces, the constants of nature, and the very structure of space-time could be seen as the incredibly complex grammar that emerged from the universe's earliest, simplest utterances. This perspective offers a dynamic and organic view of cosmic law, suggesting that the universe didn't just inherit its rules, but actively developed them from the ground up. This idea of self-organization, where complexity arises from simple interactions, finds a fascinating parallel in a powerful cosmological concept, the no-boundary proposal put forth by esteemed physicists Stephen Hawking and James Hartle. Their groundbreaking work radically redefines our understanding of the universe's beginning. Instead of picturing a cataclysmic singularity, a point of infinite density and temperature from which everything sprang, Hawking and Hartle suggest that the universe has no sharp boundary in space or time. Think of it like the surface of the Earth. There's no edge where it abruptly stops. It's a continuous, smooth surface. Similarly, they propose that the universe didn't strictly pop into existence from nothing in a singular, explosive moment. What does this mean for the emergence of physical laws? If there's no initial singularity, no distinct moment zero where everything begins, then the question of how laws manifest takes on a subtly different, yet equally profound dimension. Instead of laws suddenly appearing at a precise instant, the no-boundary proposal implies a much smoother, more gradual transition. It suggests that laws didn't need to be pre-programmed or suddenly switched on. Rather, they could have slowly coalesced and solidified as the universe expanded and cooled from this initial, boundary-less state. Imagine the universe in its earliest, most primordial phase as being somewhat like a quantum fog, existing in a realm where the distinctions between space and time, and even the very fabric of reality, were blurred. In this scenario, the laws we observe today wouldn't have been fully defined. Instead, they would have been latent potential patterns. As the universe underwent its initial expansion and began to cool, these patterns would progressively become more pronounced, much like an image slowly coming into focus as you adjust a lens. The fundamental forces, the constants that govern their interactions, and the very structure of space-time would gradually become applicable and discernible, transitioning from a state of quantum uncertainty to the classical, predictable reality we inhabit. This model allows for a truly organic genesis of physical laws. Instead of a sudden imposition, it posits a continuous, evolving process where the universe essentially writes its own rulebook as it develops. The laws would emerge not from an external decree, but from the intrinsic dynamics of the universe itself as it smoothed out and differentiated. This perspective aligns beautifully with the concept of self-organization, suggesting that the intricate symphony of cosmic physics is less a pre-composed masterpiece and more an improvisational, emergent performance, gaining clarity and structure with every passing cosmic moment. It offers a compelling way to bridge the gap between a seemingly lawless origin and the highly ordered cosmos we observe, presenting a universe that progressively defined itself. This brings us to a compelling fourth mystery in our cosmic journey, the origin of fundamental constants. We're talking about incredibly precise numbers that seem to be woven into the very fabric of our universe. Values like the speed of light, Planck's constant, the gravitational constant, or the charge of an electron. These aren't just arbitrary figures. They dictate everything from how atoms form to how stars burn and how galaxies behave. The fact that they possess the exact values they do is not only essential for our existence, but it also raises a profound question. If physical laws themselves are emergent, then these fundamental constants, which are integral to those laws, must also have emerged. Think about it. If the universe began in a truly lawless state, where even the concepts of space, time, and forces were still taking shape, then there would have been no preordained values for these constants. This implies that they weren't simply plugged in at the moment of creation. Instead, they must have somehow settled on their current precise values as the universe evolved. This notion challenges the traditional view of constants as static, unchangeable properties of reality. One intriguing idea is that these constants were not always fixed, but were instead dynamical in the very early universe. Imagine a primordial cosmic soup where these values were fluctuating wildly, shifting and settling like a chaotic dance. As the universe expanded and cooled, perhaps certain conditions or phase transitions froze these values into place, locking them into the specific numbers we measure today. This would be akin to a chemical solution that, upon reaching a certain temperature or pressure, crystallizes into a stable structure. The values we observe would simply be the frozen remnants of a much more fluid and chaotic past. This perspective opens up fascinating possibilities. Could the universe have explored a vast landscape of potential constant values before settling on the specific combination that allowed for cosmic structure and, eventually, life? This aligns beautifully with the idea of a universe undergoing a process of self-selection, where only those regions or phases that stabilize with a coherent set of constants can persist and evolve. It's a powerful idea that suggests the universe's fundamental parameters are not arbitrary, but are perhaps the result of a process of cosmic natural selection, where different values lead to different outcomes, and some combinations are simply more stable or capable of fostering complexity. Consider, for example, what would happen if the electron's charge was infinitesimally different, or if the gravitational constant varied even slightly. The intricate balance required for elements to form, for stars to ignite, and for planets to coalesce would be utterly disrupted. The very architecture of the cosmos depends on these precise settings. So, the emergence of these constants becomes not just a matter of their existence, but a story of cosmic fine-tuning, where values that could support a structured and evolving universe were somehow selected or stabilized out of a multitude of possibilities. This transformative view suggests that even the bedrock numbers of our reality are not eternally given, but are a product of the universe's own dynamic, emergent history. Building on our exploration of how fundamental constants might emerge, let's now turn our attention to one of the most ambitious theories in physics that seeks to reconcile the seemingly disparate worlds of gravity and quantum mechanics, loop quantum gravity. This isn't just about understanding forces, It's about fundamentally rethinking the very stage on which cosmic dramas unfold, space-time itself. Traditionally, we viewed space-time as a smooth, continuous fabric, like a perfectly stretched sheet. Einstein's theory of general relativity describes how massive objects warp this fabric, creating what we perceive as gravity. But when you try to apply the rules of quantum mechanics, which govern the tiny, discrete world of particles, to this smooth cosmic sheet, you run into insurmountable problems. Quantum mechanics tells us that energy and matter exist in quantifiable packets, or quanta. So, what if space-time itself isn't smooth but also granular, made up of tiny, indivisible units? This is where loop quantum gravity steps in. Imagine zooming into the fabric of space-time, deeper than we can currently conceive, far beyond the scale of atoms or even protons. Loop quantum gravity suggests that at this incredibly tiny, fundamental level, known as the Planck scale, space-time isn't continuous at all. Instead, it proposes that space-time is woven from a network of incredibly small, discrete loops, almost like an intricate, three-dimensional knitting pattern. These loops are the fundamental building blocks of space, and their connections and intersections form the very geometry of the universe. Think of it like a digital image. From a distance, it looks seamless, but up close, you see individual pixels. Loop quantum gravity suggests space-time is similarly pixelated. The profound implication here, especially for our discussion about emergent laws, is how these fundamental loops could give rise to everything we observe. If space-time itself is constructed from these discrete units, then the very laws that govern energy, matter, and their interactions, which depend so heavily on the geometry of space-time, could essentially be tied to the way these loops form, connect, and evolve. It's almost as if the laws of physics are not pre-existing blueprints, but rather a set of rules that emerge from the collective behavior and configurations of these tiny, fundamental loops. Consider how the properties of a material emerge from the arrangement of its atoms. A diamond is hard because of the strong, specific way its carbon atoms bond. Water flows because its molecules bond in a different, more fluid manner. In a similar vein, the characteristics of our universe, the way light travels, how gravity pulls, the very structure of reality, could be a direct consequence of how these space-time loops are stitched together at the most foundational level. The laws themselves would arise from the relationships and dynamics between these countless, tiny units of space-time. This theory suggests that the formation of these fundamental loops and the way they interlink at the birth of the universe essentially created the fabric of reality and, by extension, the laws that operate within it. It implies that the universe wasn't born into a predefined set of rules, but rather the rules solidified as the very structure of space-time came into being. So, the emergence of laws isn't just about abstract principles. It's about the very materialization and quantification of space and time itself, leading to a universe with the precise physical laws we now experience. Now, as we consider how these fundamental loops of space-time might give rise to physical laws, it's crucial to connect this idea with another massive concept in cosmology: cosmic inflation. This isn't just an abstract theory. It's a powerful explanation for some of the most puzzling features of our universe, features that seem almost too perfect to be coincidental. Imagine the universe shortly after the Big Bang, not even a fraction of a second old. At this unimaginably tiny moment, cosmic inflation proposes that the universe underwent an incredibly rapid, exponential expansion. We're talking about space stretching faster than the speed of light, blowing up from something smaller than an atom to potentially the size of a grapefruit in an instant. One of the key reasons scientists invoke inflation is to explain the universe's remarkable flatness. In cosmology, flatness doesn't refer to a pancake shape, but to the geometry of space itself. Think of it like this: if the universe had too much mass, its gravity would cause it to curve in on itself like the surface of a ball. If it had too little, it would curve outwards like a saddle. Our observations show that the universe is incredibly flat, almost perfectly balanced between these two extremes. Cosmic inflation provides a beautiful explanation for this. Imagine you have a wrinkled piece of paper. If you stretch it out to an enormous size, any initial wrinkles or curves would be smoothed out, making it appear perfectly flat from our perspective. Similarly, the rapid stretching during inflation would have ironed out any initial curvature in the universe, leaving us with the flat cosmos we observe today. Beyond flatness, inflation also accounts for the universe's incredible homogeneity, meaning it looks largely the same in every direction we look, even in regions that were causally disconnected too far apart to have ever interacted since the Big Bang. Without inflation, it's hard to explain how these separate regions could have arrived at such similar temperatures and densities. Inflation suggests that all the observable universe originated from a tiny, causally connected patch before the rapid expansion, ensuring uniformity. So, this period of incredible growth transformed a small, potentially chaotic patch into the vast, uniform, and flat expanse we inhabit. But how does this connect to our discussion about the emergence of laws from a lawless beginning? This is where it gets really intriguing. If we consider the possibility of a primordial lawless state, or one where laws were still coalescing, cosmic inflation could have played a vital role in setting or selecting the initial conditions from which our specific set of laws emerged. Think back to our idea of the quantum foam, a bubbling, chaotic sea of possibilities. Inflation might have acted like a cosmic filter or a cosmic oven. As the universe expanded so rapidly, it could have stretched out some of those tiny quantum fluctuations, making them macroscopic and freezing certain configurations. Essentially, by smoothing out the early universe and creating incredibly uniform conditions, inflation might have provided the perfect environment for specific physical laws to solidify and stabilize. It's almost as if the rapid expansion forced the universe to choose a particular configuration of space-time and energy from the myriad possibilities in the lawless primordial soup. This could mean that the fundamental constants which we discussed earlier and the very rules governing how matter and energy behave didn't just appear arbitrarily, but were effectively locked in or selected by the inflationary process. So, instead of laws emerging from pure chaos everywhere, inflation could have smoothed out the primordial lawlessness, creating a more stable and uniform canvas on which our specific laws could then crystallize, guiding the universe towards the predictable, ordered reality we now experience. This brings us to our fifth profound mystery. Is a law a fixed property woven into the fabric of reality from eternity? Or is it merely a dynamic relationship that emerges between particles and fields as they interact? This might seem like a subtle philosophical distinction, but it holds monumental implications for how we conceive of a lawless beginning. If laws are inherent, immutable properties, then the idea of them emerging feels almost contradictory. It would suggest they were always there, perhaps just hidden or unmanifested. However, if laws are relational, then their emergence becomes far more plausible. Consider this analogy. Think about the rules of a complex game like chess. The rules aren't inherent properties of the individual pieces themselves. A pawn isn't inherently able to move one square forward in isolation. Instead, that rule, the law of its movement, arises from the relationship between the pawn and the chessboard and its defined interactions with other pieces. The rules of chess emerge from the collective play and the established relationships within the game's system. They are not absolute properties of the individual components, but rather contextual relationships that define how those components interact. Now apply this to the universe. If physical laws are relational in this way, they wouldn't need to exist in some predetermined, fixed form before the Big Bang or before any matter and energy appeared. Instead, they could have slowly coalesced, taking shape as the universe expanded and cooled, and as particles and fundamental forces began to interact in more complex ways. Imagine a universe in its absolute infancy, a chaotic soup of quantum fluctuations where interactions are fleeting and undefined. In such a state, there might be no discernible rules because there are no stable, repeatable relationships. But as the universe evolves and as certain types of interactions become more frequent, stable, and predictable, these relationships could then crystallize into what we recognize as physical laws. This perspective suggests that physical laws aren't absolute, preordained commandments governing the universe, but rather a sophisticated form of self-organization. As elementary particles and fields begin their cosmic dance, their repetitive interactions, their pushes and pulls, their attractions and repulsions could, over time, establish patterns of behavior. These patterns, once robust enough, become the rules of the game that is our universe. The very constancy of nature, the fact that gravity always operates the same way, or that light always travels at the same speed, might be a testament not to an unchanging, pre-existing decree, but to the incredible stability and self-reinforcing nature of these emergent relationships. This view also opens the door to thinking about how laws might evolve or even differ across different regions of a massive multiverse. If laws are relational, then slight variations in initial conditions or local interactions could lead to slightly different emergent laws in different cosmic neighborhoods. It means our universe's specific set of laws might be a unique outcome of the particular path that its early interactions took. This idea transforms our understanding of laws from static decrees to dynamic, living principles, constantly being reinforced by the ongoing dance of particles and fields. It's a universe where the rules of the game are not given from the outset, but are actively learned and established by the players themselves, simply by playing. This fascinating idea about emergent relational laws naturally leads us to yet another mind-bending concept, the multiverse hypothesis. Imagine for a moment that our universe, vast and seemingly endless as it is not the sole cosmic entity. What if there are countless others bubbling into existence, each distinct, each with its own set of conditions and unique path of evolution? This isn't just science fiction anymore. Various theoretical frameworks in physics, from string theory to inflationary cosmology, increasingly suggest that our universe might be just one tiny bubble in an infinitely larger cosmic foam, a grand tapestry we call the multiverse. If laws are indeed emergent, sculpted by the specific interactions and conditions of a nascent universe, then the multiverse hypothesis gains immense traction and adds another layer of profound insight into our discussion. It means that the fundamental physical laws governing our cosmos, the strength of gravity, the speed of light, the behavior of quarks and leptons, are not necessarily universal across all possible realities. Instead, they could simply be one particular set of outcomes, one specific flavor of physics that emerged within our cosmic bubble. Think about those chess rules again. If you moved to a different game like checkers, the rules would be entirely different, even if some of the fundamental pieces were similar. Similarly, in a multiverse, each universe might have its own game rules, its own unique emergent laws. This perspective powerfully reinforces the argument that physical laws are not eternally fixed or preordained commandments etched into the very fabric of existence from time immemorial. Instead, it suggests a dynamic process where laws arise from the specific circumstances of a given universe's birth and evolution. In one universe, perhaps gravity is 1,000 times stronger, collapsing everything into black holes before stars can even ignite. In another, perhaps the weak nuclear force is so negligible that nuclear fusion never gets going, leaving a cold, dark cosmos. Our universe, then, with its finely tuned constants and laws that permit the formation of stable stars, complex chemistry, and ultimately, life, would simply be one permutation among an almost infinite array of possibilities. The implications of this are staggering. It means that the precise values of the fundamental constants we observe, often hailed as evidence of an intelligent designer or an incredibly lucky cosmic roll of the dice, could simply be a consequence of cosmic trial and error within the multiverse. Our universe just happened to hit upon a combination of emergent laws that allowed for sufficient complexity and stability to unfold. It shifts the question from why these specific laws to what kind of meta-laws or meta-principles govern the emergence of laws themselves across the multiverse. This opens up entirely new avenues of inquiry, pushing us beyond the confines of our single universe to consider the grander cosmic picture, where the very rules of reality are fluid and emergent, shaped by the cosmic dance of creation. This brings us to a profound, almost dizzying paradox. If the multiverse hypothesis suggests that laws are emergent and not universally fixed, we must then ask, what about causality itself? If we're talking about a truly lawless state, where even the most basic rules of physics haven't materialized, then the very notion of cause and effect, as we understand it, simply vanishes. Think about it. Causality hinges on predictable interactions. An action leads to a reaction. If you push a ball, it moves. This seems so fundamental to our experience of reality that it is almost impossible to imagine a universe where it doesn't hold true. Yet, in a pre-physical, lawless state, there would be no consistent forces to dictate how one event influences another. There would be no inertia, no momentum, no energy conservation in a way that generates predictable outcomes. So, how could causality itself emerge from something that is fundamentally non-causal? This isn't just a philosophical quandary. It's a monumental challenge at the very bedrock of fundamental physics. Our entire scientific methodology is built upon the idea that phenomena have causes, and that these causes can be identified, measured, and predicted. Without causality, there is no scientific method. There's no way to establish experiments, no way to test hypotheses. So, for laws to emerge from a lawless state, causality itself must have been part of that emergence. But how? How does a universe go from a state where nothing leads to anything else in a predictable way, to one where effects reliably follow causes? One line of speculative thought suggests that perhaps causality isn't an inherent, pre-existing feature, but rather a pattern that solidifies alongside the very first emergent laws. Imagine a chaotic, shimmering soup of possibilities, where events simply fluctuate without any inherent order. As certain localized patterns begin to stabilize, perhaps through quantum fluctuations, as we discussed earlier with quantum foam, these emerging patterns might create localized, transient forms of predictability. Over time, as more stable laws coalesce, these islands of predictability could expand and link up, gradually giving rise to the robust, universal causality we observe today. It's like a chaotic mosh pit, slowly, imperceptibly, forming subtle dance routines that, over vast cosmic timescales, become entirely choreographed ballets. Another perspective hints at the idea of proto-causality, where extremely weak or fleeting influences might exist even in a lawless state. These influences wouldn't be strong enough to create predictable sequences. but they could provide the barest scaffolding upon which more robust causal relationships could build. Think of it as a subtle lean that might eventually lead to a fall, but only after countless other leans and nudges begin to align. The transition from a state of pure randomness to one with even rudimentary cause and effect would represent one of the most profound phase changes in cosmic history. It's a leap from sheer chaos to the very possibility of meaning, where events start to tell a story even before the story has begun. The emergence of causality, therefore, isn't just about the rules of interaction. It's about the birth of a narrative for the universe itself. Moving from the purely physical, let's venture into one of the most speculative, yet deeply thought-provoking realms of this mystery: the potential role of consciousness itself in the creation of physical laws. This isn't about some mystical, New Age notion, but a radical concept explored by serious physicists and philosophers, often linked to idealist philosophies. The idea here is that perhaps observation, or a fundamental kind of awareness, isn't just a passive recipient of reality but actively influences, or even helps to actualize, the very laws that govern our universe. Consider the perplexing nature of quantum mechanics, where particles seem to exist in a superposition of states until observed. While this is primarily interpreted as the act of measurement affecting the system, some deeper interpretations wonder if consciousness plays a more foundational role in collapsing these probabilities into a definite reality. If quantum mechanics is fundamental to the universe at its smallest scales, could this interaction with observation or awareness have somehow contributed to the stabilization of laws out of a pre-physical, indeterminate state? It's a mind-bending leap, suggesting that the universe might not be entirely objective and independent of observers, but that some form of awareness is intertwined with its very structure. This perspective challenges our conventional understanding of reality, where consciousness is seen as a product of complex physical processes within the brain. Instead, it flips the script, proposing that consciousness, or a proto-consciousness, might be a more fundamental element, existing before fully formed physical laws and playing a part in their emergence. Imagine a primordial soup not just of energy and matter, but of potential realities where the act of observing or becoming aware causes certain patterns to coalesce and stabilize into what we recognize as consistent physical laws. It's a universe that, in some sense, wakes up to itself and, in doing so, defines its own rules. This isn't to say that human consciousness created the Big Bang, but rather that some fundamental, universal quality akin to awareness or information processing might have been a necessary ingredient for order to arise from chaos. Think of it like this: if laws are patterns that emerge from a sea of possibilities, what selects or fixes those patterns? Could it be a cosmic observer or a universal principle of awareness that guides the universe from a state of pure potentiality to one of definite physical laws? This line of thought suggests that the universe might be inherently structured to perceive and understand itself, and that this self-perception is part of how its rules became solidified. While highly speculative, this concept offers a unique lens through which to view the fine-tuning of the universe, suggesting that the precise values of physical constants and the existence of life-permitting laws might not just be a cosmic accident, but a reflection of an underlying principle of awareness helping to shape reality. It hints that the relationship between mind and matter might be far more profound and intricate than we currently grasp, making the search for emergent laws not just a physical quest, but potentially a journey into the nature of consciousness itself. It's an invitation to consider that perhaps in the very act of observing and questioning the universe, we are participating in its ongoing act of becoming. Shifting gears from the ethereal interplay of consciousness and reality, let's dive into another radical concept that redefines the very fabric of existence: digital physics. This theory posits that our entire universe, with all its intricate workings and fundamental laws, isn't some grand, analog entity, but is instead fundamentally computational. Think of it not as a boundless expanse of continuous particles and fields, but as a vast, complex information processing system, much like a super advanced computer simulation. If this is truly the case, then the physical laws we observe, from the elegant dance of gravity to the precise probabilities of quantum mechanics, aren't inherent properties of an underlying reality, but rather the coded algorithms or programs that run this cosmic simulation. This means that instead of physics being a set of immutable, pre-existing truths, it could be something that boots up or emerges from a more basic set of computational instructions. Imagine a cosmic programmer writing lines of code, and from those lines, particles gain mass, forces bind them together, and space-time itself takes on its four-dimensional structure. It's like the rules of a video game. In a game, the physics engine, collision detection, and character movements are all defined by code. Similarly, in a digital universe, the very fabric of reality, including its laws, would be the result of a cosmic code. This doesn't necessarily mean there's an external programmer in the traditional sense. It could be that the universe intrinsically processes information about itself, and these processes naturally give rise to what we perceive as laws. Consider the implications. If our universe is a form of digital computation, then its evolution, its constants, and its very structure might be determined by a set of foundational, perhaps even simple, binary operations. When we talk about laws emerging from a lawless beginning, in this context, it could mean the initial bootstrapping of these fundamental computational instructions. Picture a blank canvas of pure information, and as the initial code begins to run, patterns form, complexity grows, and the stable, consistent laws that govern our everyday experience gradually coalesce. This framework offers a compelling explanation for the fine-tuning puzzle, suggesting that the precise values of fundamental constants might simply be parameters within this cosmic program, set to allow for the emergence of complex structures, including life. This idea challenges our intuitive understanding of reality, where we often assume a continuous, analog world. But when we look at quantum mechanics, with its discrete energy levels and quantized particles, it almost whispers of a digital underpinning. Could these quantum phenomena be the fundamental pixels or bits of the cosmic computation? Furthermore, the concept of entropy, which dictates that systems tend towards disorder, finds a fascinating parallel in information theory, where increased entropy corresponds to increased information. In a digital universe, the laws would be the rules by which this information is processed, transformed, and ultimately leads to the emergent complexity and order we observe. It opens up doors to thinking about the universe's origin not just as a physical event, but as a groundbreaking act of cosmic computation, where the laws of physics are the lines of code that make it all run. This brings us to a seventh profound mystery, the arrow of time and its relationship to the development of physical laws. Our universe has a very clear direction to time, always moving from the past to the future. We remember yesterday, not tomorrow. Things break down, not spontaneously reassemble. This concept, often called the arrow of time, seems fundamental to our experience, but did it exist in a truly lawless, chaotic state that we discussed earlier, or did it emerge along with the very laws of physics themselves? Consider the implications if time's directionality is not a given but an emergent property. In a universe without laws, where everything is truly random, there would be no consistent cause and effect, no predictable sequence of events. Without these, the distinction between past and future becomes blurry, if not entirely meaningless. So, the very act of laws crystallizing from a lawless state might inherently establish the conditions necessary for time to gain its forward momentum. Imagine the universe as a complex system initially in a state of maximum disorder, where all possibilities are equally probable. As physical laws begin to coalesce, they introduce constraints, correlations, and predictable patterns. This imposition of order could be what gives time its one-way street quality. Think about it this way: the laws of thermodynamics, particularly the second law, dictate that entropy or disorder tends to increase over time in a closed system. This law is often cited as the origin of the arrow of time. If a lawless state is one of maximum entropy, then the emergence of laws could be seen as the universe beginning to organize itself, creating gradients of order and disorder that define a direction. The universe expands and cools, structures form, and complexity increases, all processes that seem to unfold in one direction. It's almost as if the universe is running a program that, once booted up, can only move forward, each step building on the last, solidifying the distinction between what has already happened and what is yet to come. This connection between the arrow of time and the development of physical order is incredibly deep. If physics itself emerged, then the very concept of before and after, of cause and effect, might be an intrinsic part of that emergence. It suggests that the forward march of time isn't an arbitrary feature, but a necessary consequence of a universe that is evolving from chaos to increasing levels of predictability and structure. The laws didn't just appear, their very appearance dictated how the universe would unfold through time, giving it a trajectory it might otherwise lack. This brings us to an eighth profound mystery, deeply intertwined with the nature of information and reality: the holographic principle and its potential connection to how laws might have emerged. Imagine a three-dimensional object like an apple. Now, imagine all the information about that apple, every detail of its shape, color, and texture, being perfectly encoded on a two-dimensional surface, like a photograph or a projection. This is the essence of the holographic principle, a truly mind-bending concept born from the study of black holes and string theory. The idea first gained traction from insights into black holes. When something falls into a black hole, it seems to disappear, yet physicists like Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to their surface area, not their volume. This implies that the information about what fell in isn't lost but is somehow stored on the black hole's event horizon, its two-dimensional boundary. Later, physicist Leonard Susskind extended this idea, suggesting that our entire universe might be a projection of information encoded on a distant, two-dimensional boundary, much like a hologram. It's as if our three-dimensional reality is a highly detailed image projected from a distant cosmic screen. This isn't science fiction. It's a serious area of theoretical physics that challenges our fundamental understanding of space and reality. Now pause and consider the implications of this for the emergence of physical laws from a lawless beginning. If our universe effectively operates like a cosmic hologram, where all the information that defines our reality is ultimately encoded on a boundary, then could the very laws of physics simply be the rules written onto that boundary? Picture a cosmic hard drive, not storing data about cat videos, but storing the fundamental algorithms and relationships that dictate how matter, energy, and space-time behave. In a truly lawless early universe, this boundary might have been featureless, a blank slate. As the universe evolved, or perhaps as some unknown cosmic process unfolded, these rules, our physical laws, could have gradually been written or etched onto this boundary. This means that the emergence of laws wouldn't be about something appearing in the three-dimensional volume of space we inhabit, but rather about the information on its two-dimensional boundary becoming increasingly complex and structured. The laws we observe would then be the manifestation, the projection of this underlying information. It would be like a cosmic printer slowly adding lines of code to a vast cosmic programming sheet. The beauty of this perspective is that it offers a way for order to arise from something that initially lacked it, not through random chance, but through the structured embedding of information. The universe, in a sense, would be booting up its operating system line by line on this fundamental information boundary. This framework also offers intriguing possibilities for why our laws are so precise. If the laws are encoded information, then their fine-tuning might be a result of the efficiency or self-consistency of that information, rather than some arbitrary cosmic dial. It suggests a deep connection between information, geometry, and the fundamental rules that govern our existence, pushing us to consider whether the universe isn't just governed by laws, but is, in its deepest essence, made of information itself. Now, let's turn our attention to yet another profound mystery that ties directly into the idea of laws emerging from a more fundamental state, the unification of forces. Imagine, for a moment, a time in the universe's infancy, immediately after the Big Bang, when conditions were so extreme that all the fundamental forces we know today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were not distinct entities. Instead, they were unified like different facets of a single, overarching cosmic force. Think of it like a block of ice. At very high temperatures, it's a liquid, but as it cools, it freezes, and distinct crystalline structures emerge. In the universe's earliest moments, when energies were unimaginably high, physicists hypothesized that these forces were effectively indistinguishable, acting as one. As the universe rapidly expanded and cooled from this incredibly hot, dense state, a series of crucial events, often called phase transitions, began to occur. Much like water transitioning from steam to liquid to ice as it cools, these unified forces are theorized to have successively broken symmetry, separating into the distinct forces we observe in our universe today. First, gravity might have split off from the others. Then, the strong nuclear force which binds atomic nuclei together would have separated. Finally, electromagnetism, responsible for light and electricity, and the weak nuclear force which governs radioactive decay would have gone their separate ways. Each of these unifications breaking apart or coalescing into distinct identities fundamentally shaped the laws that govern their interactions. This process of force unification and subsequent separation offers a compelling narrative for how our familiar physical laws could have emerged. It suggests that the laws weren't always there in their current form, but rather crystallized from a more symmetric, simpler, yet far more chaotic primordial state. The very act of the universe cooling and expanding would have provided the conditions necessary for these fundamental interactions to differentiate and define themselves. It's like the universe was slowly revealing its rules as it matured, with each phase transition specifying another layer of physical law. Consider the profound implications. If the universe had cooled differently, or if the initial energies were slightly varied, these phase transitions might have unfolded in a different order, or the forces might have taken on slightly different characteristics. This could lead to a universe with an entirely unique set of laws, perhaps one where matter couldn't form or stars couldn't burn. This perspective deeply connects the emergence of our physical laws to the dynamic evolution of the cosmos itself, rather than seeing them as fixed constants from eternity. It underscores the idea that the laws we observe are not arbitrary. but are intrinsically tied to the universe's journey from an incredibly energetic, unified beginning to its current diverse and structured state. This ties law emergence directly to the grand narrative of cosmic evolution, turning the very structure of reality into a dynamic process. This brings us to a fascinating concept of what we might call the metaphysical inertia of laws. If these fundamental forces and constants weren't there from the very beginning, if they truly emerged from a more chaotic state, why do they seem so unyielding now? Why do the laws of physics remain constant, governing everything from the smallest subatomic particles to the largest galaxy clusters, without apparent change over billions of years? It's almost as if, once these laws coalesced and found their specific forms, they gained a kind of inherent permanence, a cosmic resistance to alteration. Think of it like a river carving its path through a landscape. Initially, the water might meander, exploring different routes through soft soil. But once it hits bedrock, it establishes a deep, enduring channel that becomes incredibly difficult to change. The forces that shaped the initial path are dynamic, but the resulting riverbed gains a stability, a kind of geological inertia. Similarly, perhaps the universe, in its earliest, energetic moments, experimented with various possible configurations of forces and constants. But through processes like symmetry breaking and phase transitions, a specific, stable set of laws froze out, becoming the fundamental bedrock upon which all subsequent cosmic evolution would unfold. This suggests that the universe essentially chose or settled on a particular set of rules that were robust enough to persist and allow for the complex structures we see today, from stars to conscious beings. This concept of metaphysical inertia implies that the laws themselves are not simply static decrees handed down from eternity, but rather outcomes of a dynamic, formative period in the universe's history. Once established, however, these emergent laws become the scaffolding of reality. They dictate how matter behaves, how energy transforms, and how structures form. This stability is crucial for everything we observe. Without it, the universe would be an unpredictable mess, incapable of forming stable atoms, much less planets or life. It's this enduring nature of the laws that allows for cosmic evolution to proceed in an orderly fashion, ensuring that the universe remains comprehensible and predictable within its established framework. The implications of this inertia are profound. It suggests that while the universe may have begun in a state of lawlessness, the very act of emerging into laws imbued them with a self-sustaining quality. This isn't to say they are absolutely unchangeable, as some speculative theories propose extremely slow, almost imperceptible variations in constants over cosmological timescales. But for all practical purposes, and certainly for the lifespan of our universe, these laws act as unshakable pillars. Their stability allows for the long-term processes of stellar nucleosynthesis, galaxy formation, and ultimately, the intricate chemical reactions necessary for life. It's a testament to the universe's self-organizing capacity, producing a stable, rule-bound reality from a state that, by definition, had no rules at all. This leads us directly to the ninth major mystery we're exploring: the profound role of self-consistency in the formation and persistence of physical laws. If these laws truly emerged from a dynamic, lawless past, could it be that the laws we observe today, the ones that govern our universe, are simply those that are inherently stable and internally self-consistent? It's a compelling idea, suggesting a kind of cosmic quality control, where only the most robust and coherent sets of rules could endure and allow for the complex evolution of reality. Imagine a vast cosmic testing ground where countless proto-universes or pockets of emerging laws spontaneously form. Some might develop rules that are contradictory, leading to instant collapse or a chaotic state where nothing can truly coalesce. Perhaps a rule dictates that matter attracts, while another demands it repels, leading to immediate annihilation. Other sets of rules might be unstable, fluctuating wildly, preventing the formation of stable structures like atoms or stars. These universes, with their inconsistent or unstable laws, would be stillborn, unable to sustain themselves for any meaningful length of time, if they even got off the ground at all. Our universe, however, exists. It has endured for billions of years, giving rise to intricate structures and life itself. This points to a fundamental self-consistency within its physical laws. The laws of gravity, electromagnetism, and the nuclear forces, along with their associated constants, work in harmony. They don't contradict each other. Instead, they intertwine in ways that allow for the formation of stable particles, the fusion of elements in stars, and the delicate balance required for planetary orbits. This internal coherence isn't random. It's a prerequisite for any enduring structure. This concept bears a striking resemblance to natural selection, but applied to the very fabric of reality itself. In biological evolution, organisms with traits better suited to their environment are more likely to survive and reproduce. Here, we might envision a similar process for laws, only those sets of fundamental rules that are internally stable, consistent, and capable of generating a universe that doesn't immediately unravel would be selected for persistence. The unfit laws, the contradictory or unstable ones, simply wouldn't last. This isn't a conscious selection, of course, but an inherent consequence of the law's own properties. So, the laws we observe might not just be arbitrary choices from an infinite menu of possibilities. Instead, they could be the successful survivors of a cosmic trial and error process, the robust rules that allowed for a stable, evolving cosmos. This perspective imbues our laws with a deeper significance. They are not merely descriptions of reality. They are the very conditions that make reality possible, a testament to the universe's inherent drive towards stable order. It suggests that consistency and stability are not just properties of our laws, but perhaps the foundational principles that allowed them to emerge and endure in the first place. Beyond the idea of laws being selected for their self-consistency, some of the most mind-bending cosmological models take us even further back, suggesting a reality that wasn't born from absolute lawlessness, but rather from a continuous, perhaps endless, cycle of cosmic events. These are the pre-Big Bang scenarios and the concept of cyclic universes. Instead of our universe springing into existence from a singular, isolated event, these theories propose that our Big Bang was merely one in a long, perhaps infinite, series of expansions and contractions, bounces or transitions. Think of it like a cosmic accordion, constantly expanding and then collapsing back in on itself, only to rebound into a new expansion. In such a grand, eternal dance, the concept of physical laws doesn't necessarily have to emerge from an ultimate void of rules. Instead, these laws might evolve over vast cosmic eons, or they could get rebooted with each new cycle, carrying some kind of subtle memory or inheritance from the previous iteration. This profound idea challenges the notion of a truly lawless beginning, offering a different pathway for the emergence and evolution of the very rules that govern existence. One popular example of such a model is the ekpyrotic universe theory, which posits that our universe arose from the collision of two three-dimensional brains in a higher dimensional space. This collision would generate the Big Bang, but instead of being a unique event, it would be part of an ongoing cycle. In this framework, the laws that govern our universe might not be entirely new with each bounce, but could be refined or subtly altered versions of the laws from the preceding cycle, gradually converging on a set of stable, consistent rules over immense durations. It's as if the universe is running countless experiments, slowly perfecting its own operating system. Another intriguing consideration is how such a cyclic model might address the fine-tuning problem, where the fundamental constants of nature seem perfectly set for the emergence of life. If laws and constants are inherited or evolve across cycles, then a vast number of previous iterations could have explored different sets of parameters. Our universe, then, would be the one that emerged from a cycle where the conditions were just right, or perhaps even improved upon, allowing for its complex structure and the eventual appearance of conscious observers. This offers an alternative to the Anthropic Principle, suggesting an iterative refining process rather than just a lucky draw from a random distribution. The implications for the emergence of laws are profound. Instead of a single moment of law genesis from nothing, we might be looking at a continuous, dynamic process where laws are constantly being tested, adapted, and passed on. This could explain the remarkable stability and coherence of our laws, not just as a result of self-consistency, but as a product of eons of cosmic evolution, where less stable or less conducive laws simply failed to perpetuate themselves into the next cosmic iteration. It paints a picture of a universe that learns and adapts, with its fundamental rules being the culmination of an unimaginably long cosmic history. This brings us to our 10th mystery. If laws are truly emergent, why did these specific laws emerge in our universe and not an infinite number of other possibilities? This isn't just about observing the universe as it is. It's a deeper dive into the very principles or meta-laws that might govern the emergence of laws themselves. It asks us to look beyond the what and consider the why of cosmos. One intriguing perspective is that the laws we observe are simply the most stable or self-consistent ones. Imagine a cosmic natural selection at play. If countless proto-universes or cycles could give rise to different sets of laws, perhaps only those laws that are internally coherent and robust enough to allow for a stable, long-lived universe would persist. Laws that lead to immediate collapse, infinite expansion without structure, or simply fizzle out, wouldn't allow for anything interesting to happen, let alone for conscious observers to emerge and ponder their existence. So, our universe might simply be the one whose emergent laws are best suited for longevity and complexity. Another possibility ties into concepts like the landscape of string theory. Some physicists propose that there's an enormous number of possible universes, each with its own unique set of physical laws and constants. If so, our universe would simply be one tiny patch in this vast landscape, a particular valley where our specific laws settled. But this still leaves us with the profound question of how our particular valley was chosen or generated. Was it pure chance, or is there some underlying mechanism, almost a cosmic algorithm, that guides the emergence of laws to certain configurations? This idea pushes us to consider what principles might govern the selection or manifestation of these diverse sets of rules. It's also worth considering whether the very act of physical interaction plays a role in solidifying these laws. If laws aren't preordained but arise from the dynamic interplay of fundamental components, then perhaps the specific patterns of interaction in our early universe led to the particular laws we see today. This is like a complex dance where the steps themselves define the rules of the dance. In this view, the universe isn't just following rules, it's actively creating and refining them through its own cosmic evolution. This makes the question of why these laws less about a pre-existing blueprint and more about the historical pathway our universe took, ultimately, this 10th mystery challenges us to think about a level of reality even more fundamental than our physical laws. Are there deeper principles that dictate which laws can emerge, or even a system that learns from previous cosmic iterations, slowly refining the rules of existence? This line of inquiry delves into metaphysics, theoretical constructs, and perhaps future discoveries that could reveal if our laws are universal necessities, cosmic accidents, or products of an ongoing, dynamic process. It suggests that the quest to understand why our universe operates the way it does is far from over, and the answer might lie in a deeper understanding of how order arises from infinite possibilities. The profound questions we have just explored naturally lead us to consider how we might ever truly test these wild ideas about emergent laws. This is where advanced computer simulations enter the picture, offering a tantalizing possibility for physicists to model hypothetical universes with varying initial conditions. Imagine being able to set up a digital cosmos, tweak its fundamental parameters, and then let it run to see what kind of physical laws, if any, emerge from the initial chaos. These simulations aren't just theoretical musings. They are becoming increasingly sophisticated, allowing us to explore scenarios that are impossible to replicate in a laboratory or observe directly in our own universe. Could we one day build a simulation powerful enough to truly model the emergence of physical laws from a truly chaotic or undefined state? This isn't about simulating a universe that already has known laws, like modeling a galaxy formation or the behavior of black holes. Instead, it's about starting with a digital nothing, or perhaps a primordial soup of undefined computational elements, and observing whether stable, recognizable laws spontaneously coalesce. If such simulations could demonstrate that physical rules can indeed arise from a lawless beginning, it would provide a powerful form of empirical evidence for these theoretical concepts, moving them from the realm of pure philosophy into the domain of testable science. It would be akin to watching a digital Big Bang unfold, not just creating matter and energy, but forging the very rulebook of reality itself. This pathway offers a revolutionary method to test ideas that previously resided solely in the mind. For instance, we could program a simulation with the principles of quantum foam, as discussed earlier, and observe if stable configurations or effective smooth spacetime regions emerge with consistent properties that resemble our own universe. We might even be able to experiment with different initial conditions or algorithms for the cosmic natural selection of laws. By varying the parameters that govern the early, undefined state of these simulated universes, we could gain insights into which types of chaotic beginnings are most likely to yield ordered, law-abiding cosmoses, and which simply dissolve into formless noise. Moreover, these simulations could help us understand the role of self-organization, allowing us to see if complexity and predictable patterns spontaneously arise from simple local interactions without any preordained grand design. If we can observe digital laws solidifying from the dynamic interplay of fundamental computational elements, it would lend significant weight to the idea that our universe's laws aren't eternal blueprints, but rather emergent properties of its historical evolution. This digital experimentation allows physicists to be cosmic architects, not just observing reality, but actively constructing and deconstructing hypothetical realities to see what makes them tick, and more importantly, what makes them exist in the first place. This quest to understand how laws might have emerged from a lawless beginning truly pushes the boundaries of scientific inquiry in unprecedented ways. It's not a question that can be answered by one discipline alone. Instead, it demands a grand synthesis of some of the most profound theories in modern physics. We have to weave together the mind-bending principles of quantum mechanics, which govern the incredibly small and the probabilistic nature of reality, with the majestic scope of general relativity, which describes gravity, space-time, and the very largest structures of the cosmos. But the puzzle doesn't stop there. This line of questioning also necessitates a deep dive into information theory, exploring how order, patterns, and rules can arise from raw data, or even from the absence of it. But even this powerful combination of existing frameworks might not be enough. The very idea of emergent laws suggests that we might need entirely new conceptual frameworks, ways of thinking about reality that go far beyond our current understanding of particles, fields, and forces. Imagine a field of physics dedicated to pre-physics, an exploration of the conditions and mechanisms that allow physical laws to crystallize into existence. This isn't just about tweaking existing equations, it's about fundamentally rethinking what a law even is, and how something so foundational could have a genesis. This journey promises to redefine our understanding of what physics is at its very core, shifting it from a study of eternal rules to an exploration of how those rules came to be. It could transform our perception of reality from a static, pre-programmed universe to a dynamic, ever-evolving tapestry where even the rules themselves are part of the cosmic dance. This profound exploration might lead us to a universe that is far more self-organizing and adaptive than we ever conceived. If laws are not immutable blueprints but emergent phenomena, then our cosmos might possess a deeper, intrinsic capacity for self-creation and evolution, not just of life forms or galaxies, but of the very principles that govern them. This isn't just an academic exercise, it's about understanding the ultimate origins of everything around us, from the glow of a distant star to the intricate dance of atoms within our own bodies. It forces us to confront questions about contingency versus necessity, about whether our universe is one of many possible realities, or if there's some underlying principle that selected our particular set of laws from a vast cosmic menu. The implications for philosophy, for our place in the universe, and for the very meaning of existence are simply staggering. The profound implications of laws emerging from a lawless beginning challenge our deepest assumptions about the universe, reshaping our very understanding of what reality is. It suggests that the cosmos is far more dynamic and less predetermined than we might have ever imagined. This paradigm shift opens up tantalizing possibilities, not just for cosmic evolution, but for the very nature of existence itself. If the rules of the game weren't handed down from eternity, but instead arose from a primordial state of chaos, then the universe possesses an inherent creativity, a capacity for self-organization that goes far beyond simply arranging pre-existing components. This journey to uncover these mysteries is truly far from over. We are only just beginning to scratch the surface of what it means for physical laws to be emergent. It compels us to rethink concepts like determinism versus free will, the role of chance, and whether there's an ultimate purpose to the universe. If laws are not fixed but capable of change or evolution, then the universe becomes a living, breathing entity, constantly defining and redefining itself. This isn't just about abstract physics. It touches upon the very fabric of our being, making us wonder if the laws governing our own existence are also part of this grand cosmic dance of emergence. We've journeyed through the mind-bending concept of a universe where physics itself emerged from a lawless abyss, tracing its path from the turbulent quantum foam to the precise parameters illuminated by the Anthropic Principle. Along the way, we've explored profound mysteries that continue to challenge our understanding of reality. The notion that order can spontaneously arise from absolute chaos is not merely a theoretical exercise. It profoundly reshapes our understanding of cosmic origins and the very fabric of fundamental reality. This ongoing scientific quest, this relentless pursuit of knowledge, urges us to remain perpetually curious, to question everything we once considered immutable, and to marvel at the extraordinary elegance that somehow emerged from the most improbable of beginnings. It is a testament to the universe's incredible capacity for self-organization, turning what appears to be an initial void into a cosmos teeming with intricate laws and breathtaking phenomena. If this exploration into the deep, unexplained workings of the universe has ignited your own cosmic curiosity, we invite you to consider subscribing for more journeys into the unknown. We're constantly delving into the biggest questions about space, time, and existence itself. We'd also love to hear your thoughts. What does a lawless beginning truly mean to you? Share your ideas and reflections in the comments section below. Your insights help us all ponder these grand mysteries together.